Good morning, one and all. My name is Swati, Assistant Professor from CSC Department, PVRIT Narsapur. Today, I would like to explain about traveling salesperson problem from dynamic programming. This is one of the important application in dynamic programming. If you see the previous year question papers, at least one question will be asked from traveling salesperson problem. Before explaining about this problem, I would like to explain one example and I would like to relate that example with traveling salesperson problem. So first we'll see one diagram. In class, before explaining about this traveling salesperson problem, I have shown this diagram to the students. Even we also solve these kind of things in newspapers, Sunday books, and also in magazines, right? Even students also show an interest to know, how ma'am will relate this diagram with the traveling salesperson problem. So, after showing this to the students, I asked them that what you observe from this diagram and what we have to do here. Nothing but how to solve this one, like I asked them a topic. So some students said that we have numbers, different numbers here, and some students said that to get a proper picture, we have to connect all these numbers. And some students said that in order only we have to connect. If we will not follow the order, we may not get the proper picture. And some said that we have to start from number one and we have to reach back to the same number by connecting all other numbers. So finally, after all these solutions, we have concluded that here to get a proper picture, we have to start from number one and we have to connect all other numbers and we have to reach back to the same number where we have started. And while connecting, we have to be clear that each number will be connected only once. If we connect multiple times, we may not get the proper diagram. So this is the conclusion given by the students. So based on that, I just related all these this example with the topic. So I picked all the solutions or all the answers which are given by the students. And then to explain about the traveling salesperson problem, I have taken one graph. So here in previous example, we have the numbers and those will be connected, but here we have a graph with four nodes. So here traveling salesperson problem is also same like the previous example. Here we are going to start our tour from node 1 and we have to visit all other nodes only once and we have to return back to the same node where we have started. So simply traveling salesperson problem is used to find a minimum cost tour. Here tour is nothing but a path which is starts and ends at same vertex by visiting all other vertices only once, right? So here the cost will be calculated by adding the cost of all the edges on the tour. So here the main problem here is whenever we start the tour from vertex 1, we have to, we may go to vertex 2 first, or we may go to vertex 3, or we may go to vertex 4. Nothing but here we have many possibilities to complete our tour, right? So from all these possibilities, we have to find out one possibility which is giving the minimum cost. So that we have to find out. So to find out that we have a formula which will give the optimal traveling salesperson tour. So here this is the formula. G is nothing but graph and V are nothing but vertices. So here we have to find out a optimal tour from vertex 1 to vertex 1 by visiting all other vertices. Nothing but except this one. Whatever the vertices we have to visit all those. But in what order we have to visit? That is the main thing or main problem we have here. So to find out that, we have the formula. Here we have taken some vertex k. This k is nothing but it is a vertex from vertex 2 to n. So here in this example, from vertex 1 to 1, if we want to move, we have to visit the three vertices, that is 2, 3 and 4. So in what order it has to be visited, that we can to find out that, we can use this formula. So here why I have taken minimum of the minimum condition means, here we'll get the three possibilities, right? So from vertex 1, either we can move to vertex 2 or vertex 3 or vertex 4. So from these three possibilities, which is giving the minimum cost, that will be the best one and that will be chosen here. So by using this formula, we can find out the optimal tool which is giving the less cost or minimum cost. So normally, whenever these kind of questions will be given in the exam, student will get confused too, or students will feel somewhat difficult to remember these formulas. So if we'll explain this with a simple example, it is easy for them to remember. So we'll solve one example by using this formula so that it is easy for the students to remember. So we'll see one example. So here question is given that we have to find out optimal tour for given graph from vertex 1. So nothing but here we have to start the tour from vertex 1 and we have to visit all other vertices only once, and we have to reach back to the same vertex where we have started. So to solve this question, first of all, we have to find out the cost adjacency matrix. Cost adjacency matrix is nothing but here it represents the cost from one vertex to other vertex, which is represented in this graph. So in this graph, the cost from vertex 1 to 2 is 10, so that we have represented in first row, second column in this cell. Similarly, from 1 to 3, we have represented in first row and third column. So like this, we have represented all vertices cost in 4 by 4 matrix. Because here we have taken only 4 vertices, no? So we need 4 by 4 matrix. If we have 5 vertices, we have to take 5 by 5 matrix. So by using this cost adjacency matrix, we can solve the problem. But here, what we have to do, first of all, to solve or to find optimal tool, what we have to do. So main result we have to get is from vertex 1 to 1, in what order we have to visit all these intermediate vertices. Again, I mean, as I said, here we have three possibilities. Either from vertex 1 to 2 first we can move, and 2 to 1 by visiting all other vertices. I mean nothing but other than this 1 and 2 which are already visited. Okay. Otherwise, we have one more possibility. We can start from vertex 1 and we can move to the vertex 3, and from 3 to 1 by visiting unvisited, the vertices which are not yet visited. Or one more possibility is we can move from 1 to 4 and 4 to 1 by visiting the vertices which are not yet visited, right? So here all these red color values we can get from the cost adjacency matrix, because these are the direct values cost from vertex 1 to 2 that we have represented in adjacency matrix. But here, how to calculate this one? Again, to find out the path from 2 to 1, we have two intermediate vertices, right? Here also we will get two possibilities. Either we can move from 2 to 3 first, or 2 to 4. So that we have to represent. So we can simplify this equation in this format. So either we can move from 2 to 3 or 2 to 3 and 3 to 1 with intermediate vertex 4, or else one more possibility is 2 to 4 uh, and and 4 to 1 with one intermediate vertex, that is 3, which is not yet visited. So similarly here also we have two possibilities. Either 3 to 2 we can move, or 3 to 4 we can move. And here also we have two possibilities, that is 4 to 2 we can move, or 4 to 3 we can move. So these are all possibilities. And again, to find out the value of this equation, this means here only one intermediate vertex we have, so directly we can move from 3 to 4 first and 4 to 1 without any intermediate vertex, because here vertices are not left which are not yet visited. So here that's why I have represented with pi. Okay. So here it is a path from 4 to 1 directly without any intermediate vertex. So similarly, this equation is also simplified like this. So 4 to 3 directly we can move, again 3 to 1 without any intermediate vertex, and this one is also simplified like this. And all this we can simplify by using the formula. So here, how to find out this value? Here direct value we are finding nothing but the path from 4 to 1 directly without any intermediate vertex. So it means it is C41, which we have in cost adjacency matrix. So directly we can take this value from cost adjacency matrix and we can substitute that in this place, and after adding these two values we'll get the value for the above equation. So like this we can find the solutions for all this. So after substituting all these values, we'll get the solution for the above equation. And similarly, after adding these two, we'll get the solution for the above equation. So like this, here we are representing all the possibilities, and after solving all possibilities, we'll get the minimum cost tool for our problem, right? So here, if we'll explain the procedure in this manner with this example, I think it will be easy for the students to remember. So we'll write all the possibilities in a proper way. So here, without any intermediate vertices, any intermediate vertex, all the possibilities I have represented 2 to 1 direct path. So these values we have taken from the cost adjacency matrix, and again with one intermediate vertex all the possibilities I have represented, and these also we have solved by using the formula. All these values we have taken from the cost adjacency matrix, and these values 3 comma 1 direct values we have taken from the previous solvation. And similarly with two intermediate vertices, all the possibilities we have represented. And in this we got the minimum value 26 from the path 2 to 3, 3 to 1. And similarly from 3 to 1 with two intermediate vertices, the minimum value is 22 that we got from this path. And again here 4 to 1, we got the minimum value that is 23 from this path. So all the possibilities we got here. So from all these values we can find the solution for the main problem, that is from 1 to 1 in what order we have to move. So after substituting all these values we got the minimum value that is 36 from the path C of 1 to. So here one path we we got, that is from 1 to 2 we have to move. Again 2 to 1 how to reach, nothing but 2 to 3 or 2 to 4 which we have to move first, that we can find from the previous solvation. So here we got the minimum value for 2 to 3. So again so here we finalize that 1 to 2 we have to move, again 2 to 3, again 3 to 4. So that we can find from the previous solvation. And again here also 4 to 1 direct path we can find out from the previous solvation. So here after finding all the solutions we got the minimum cost path, that is 1 to 1 through intermediate vertices 2, 3 and 4 with minimum cost that is 36. So this is one example for the students. And the real-time applications, so this traveling salesperson algorithm will use in transportation. So mainly if you want to find out a path, if I want to go to any tour, so I have to start from my home and I have to go, I have to visit many places and I have to return back to the same place where I have started, right? So in that case we can use the traveling salesperson problem, which reduces the time and also the cost. And the second application will be IC design. When we are designing the internally we have many circuits. All these will be connected through wires, which we'll call it as a routing. For internal routing purpose, we'll use the traveling salesperson algorithm, because with this the shortest distance will find out, so that the time or power consumption will be reduces.